All right. Hello, everybody. My name is Janette Levin. I am a fourth year PhD student at Brown working with Alex Evans. And as was just said, I'm here to talk to you about constraining the creep content of IMBRIUM EJECTA. So as one of the previous talks really nicely set me up for this, I'm not going to really talk too much about what creep is. But what I will tell you is that the IMBRIUM Basin, which is one of the youngest giant basins on the moon, happens to be right in the center of the Procellarum creep terrain. So there has been a connection between the IMBRIUM basin and the thorium distribution of the surface, as was mentioned earlier, thorium being a proxy for creep, that has been known for several decades now. And previous workers have hypothesized about how this happened, and likely that the IMBRIUM impactor must have impacted into some sort of reservoir and just redistributed some sort of thorium-rich material across the surface. However, there's not really been any constraints that have been placed on this material because the concentration, the distribution of thorium is really known only for the surface. We don't have a great understanding of how thorium varies once you start going into down in the down direction. So a work that I have in progress that is currently going through the review process has been using complex craters to place vertical bounds on the thorium distribution. I'm actually not going to go into that whatsoever right now because I don't have time. And I would rather dig into some of the results that we found, but I'm happy to chat afterwards if anyone has questions. So the first thing I need to introduce here will be one convention that I'm using. I have divided the lunar surface into these 4 quadrants centered on IMBRIUM. So in all of my plots, you will see 4 different symbols. They each correspond to one of these quadrants. This is so I can more accurately find regional trends that happen as a function of distance from IMBRIUM, as opposed to them getting just kind of averaged out into one big global average. So here, what this plot on my right is showing is measurements that we have made for bounds of a sample layer of thorium enriched material. So on the top, we have a maximum thickness, and on the bottom, we have a minimum thorium abundance. So what we're trying to do is understand how IMBRIUM can contribute to this. And in order to do that, we are going to use EJECTA modeling of the IMBRIUM impact to relate thickness and thorium abundance to one another. So this is following after the work of Larry Haskins, who was a professor here for many years. But using ballistic sedimentation, we can find the proportion in the total deposit of. So let me back that up just a tad. So in any location for a giant impact such as this one, your total deposit is going to be composed of 2 components. There's going to be the primary material from the actual impact, but then there's also going to be a large amount of local material that was kicked up when that primary material arrived. So the total deposit here shown in the black line, local material in the dashed, and the primary ejecta in the dotted. So and you can see that for most of the moon, the local material is actually what is dominating that total deposit. So when we compare our measured bounds to this plot, we find that, for example, for almost all distances, these bounds are actually above the expected total deposits of IMBRIUM. So that's a good first step that this is not completely fruitless. So from there, what we can do is essentially turn it into a volumetric mixing problem. So we're essentially just trying to figure out what would be the abundance of the primary ejecta that would most accurately recreate the thorium distribution across the lunar surface. So at all distances from IMBRIUM, we know the thickness of the local materials, and we know the thickness of the primary materials. So assuming, which is an assumption, of the local materials have a abundance of 0.63 with parts per million, which is the Highlands bulk average, I believe. We can then try to use our measured bounds to find the best fit primary ejecta abundance. So in order to kind of limit our study to regions that are most likely to just have signal from that, we're actually excluding the entire IMBRIUM continuous ejecta. We are also only fitting between that. So you see the two blue circles on the map. The smaller one is the outside boundary of the continuous ejecta, and then the larger one is the minimum modeled thickness, which puts it well outside of the bounds of the South Pole Aitken Basin. So we're also masking out any pixel that has overlap with a lunar maria, as those are basaltic materials, and we do not want them contributing to this estimate of the ejecta materials. So once we do that, we find that the best fit for thorium material of for the thorium abundance of the IMBRIUM primary ejecta is 34 parts per million, which is quite a bit higher than anything that you see on the lunar cross-sector gamma ray spectrometer map. So this black line that is over here is showing the expected distribution that such a primary ejecta would create across the surface. And the gray bar shows our 200% error. So the bottom of which being 15 parts per million, the top of which being 54 parts per million. So the fit aside, there's some very interesting regional trends that pop out when you look at this. So the first one that I'd like to direct your attention to is this one on the very antipode over here. Is this thing got a laser pointer? It's not. Whatever.
Oh, it should be on there.
That's just not the right button. It's okay. So I have a finger and I will point, and there is a blue arrow. So if you look at these values at around the 4,000 to 5,000 distance from IMBRIUM, there are values of thorium abundance that are higher than even our highest error bound of 54 parts per million. So if you compare that distance to what is happening on the map on the right, you know that these are the values inside of the South Pole Aitken Basin. So this pretty definitively shows that there's no way that the IMBRIUM ejecta alone could have created that signal in the South Pole Aitken. That's just, it would have needed help. So it also gives you some sort of understanding of how much you can be expecting from IMBRIUM material to be contributing to that area. A similar situation is happening at around this 2,000 kilometer distance. They're not exactly the easiest to see, but the 2,000 kilometer contour on the map corresponds with the border of the PKT. And so particularly the values in the third quadrant and the fourth quadrant, so on the southern border, seem to be higher than our errors would explain. So there is definitely some non-IMBRIUM thorium enrichments happening there. So to kind of summarize, from our database that we have created that estimates the vertical distribution of thorium on the moon, we have found that the IMBRIUM ejecta is most likely, must have been higher than 15 parts per million thorium abundance. So from there, we can then make predictions about the expected target material that IMBRIUM would have impacted into, which involves a whole slew of other assumptions and interesting conversations. The other thing that we are able to definitively say is that the IMBRIUM ejecta alone does not explain the elevated thorium within the South Pole Aitken Basin and along the south edge of the Procellarum creep terrain. So with that, I think I went way faster than I thought I would, but that is okay. So I can take some questions.
Questions in the room?
Surprise. It was a really neat study. So the Apollo 14 site is a pretty good site for looking at what we might think of as sort of pure IMBRIUM ejecta. And it's about 13 to 15 ppm thorium. So, that 15 ppm thorium doesn't surprise me, but a little higher than that is hard to figure. So I don't know, what are your thoughts about that?
So so those higher values have been really interesting, and I think at least part of them is going to be coming out of the way that we are finding those bounds, and those are again bounds. But I really am not a mineralogist by trade, so what I've been trying to work out is how much of this could be attributed to values that have been heightened due to just the spatial deconvolution technique that we've been using. and how much of it could be values that are higher in thorium, such as we have found higher values that as you very recently told me, were not necessarily creep, but maybe there were enriched thorium silicic locations that also mixed in somehow. But it's not out of the question that there was material that had higher thorium enrichments on the moon. How exactly it made it into there is not a question that I'm equipped to answer, but I would love to hear people's thoughts about how else that could have happened. That's not fair. You're on this talk.
It's a related question
Mhm.
because the 15 parts per million, that's the IMBRIUM ejecta as a whole. So when you back out that source material that IMBRIUM had the impact, what are those numbers?
They go up even higher, and as both you and Brad probably remembers, that if you try to back out the creep reservoir values, then they go up significantly higher. And I think we got values between like 47 parts per million and 120 parts per million, which really suggests a really, really thorium intense creep reservoir. But again, I'm doing some extra statistics on those to see where those error bars could be. So please hold on the definitive answer to that question. But exactly how you can get values that are that high. Question to the petrologists and mineralogists in the room, really. I am a humble statistician.
So the highest thorium impact melt breccias that are actually found at Apollo 12 are about 30 to 35 ppm thorium.
Mhm.
And so that could be source material.
Yeah, so I guess that's good information for me to remember, or
That's
remember
rare.
that I have.
That's the only place they've been found so.
Mhm. Because I think, if I remember correctly, there are silicic materials that are way higher. Yeah, but I don't know how much of those you could expect and where exactly they were sourced from, because